This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, right. I started recording now, so I think we should start. Okay, thanks guys for coming to lecture, 5 p.m. lecture especially. I know by the end of this lecture you all will be thinking about dinner, so I'll try and be quick and hopefully you can cover some stuff today, right? Some good material. Right, so before I start, a bit of announcements. You guys basically confused me on Monday, right? But now I'm quite sure that Practical 1, all right, P01 is your MATLAB workshop, okay, which is the one which is not compulsory, and it starts from week 3 to week 5. Have you all managed to register for this workshop? Okay, all right, I see one or two hands who are not able to, but I hope majority of you have been able to register for this session. If you have not, please drop me an email, all right, and I'll see what I can do. Right, so if you look at your timetable, if it's P01 here, it's going to be your MATLAB workshops, all right, and it's at EDS 5. And it's from week 3 onwards, week 3 to week 5, right? And the airfoil lab is your Prac 2, okay? Again, those of you who cannot register for this practical, please send me an email, all right? Because I'm pretty sure we have sufficient space, okay? You only have to attend one session, by the way, all right? Just one session, and it starts from week 3 onwards, right? So I know some of you might get a bit confused. So basically, if you see if it's P02, oops, right? So that's your airfoil lab, okay? And 14 is the session number that you're in, all right? And the date for your prac, right, is going to be dependent on what section you're in, okay? So for section 14, it's going to be on the 20th of August, right? And this venue is the airfoil lab, sorry, in the Walter Bassett Aerodynamics lab, okay? If anyone comes and asks me, where is this departmentally organized venue, hell, I will tell you the wrong location, okay? You should know that this is going to be a Walter Bassett lab. Everyone clear? Right? Okay, so if you have not registered to any sessions, either your Prac 1 or Prac 2, send me an email, okay? Right, so just a quick recap on what we did on Monday. So the overarching goal of this subject is to predict the forces and the flow field around an airfoil. And broadly speaking, there are 3 approaches which you can take. Right, the first one is experimental, where you'll be doing some scaled laboratory experiments in the airfoil lab, right? Computational, which is my area of research. So basically, I'm using computers or high-performance computers, right, to solve the Navier-Stokes equation, right, which is also known as computational fluid dynamics, right? And the approach which you'll be taking in this subject would be analytical, where we'll be simplifying. We're not going to solve the Navier-Stokes equation. We're going to simplify it first, and then we're going to solve the Navier-Stokes equation, all right? So we started off with this big, ugly equation, right? But theoretically, it's actually not that complex, right? It's basically the conservation of linear momentum and the conservation of mass, okay? And we're going to start chopping out terms from this equation. So one of the first assumptions that we make to simplify this equation so that we can solve it using a pen and paper is to assume that the flow is two-dimensional. Right. So basically, if you have a flow over an airfoil, we are going to contain the flow in the XY plane. Okay, and it basically means that the flow is going to be the same at all Z locations. All right, at all span-wise location, the flow is invariant, it's the same, okay, for a two-dimensional flow. Now, when when we make this assumption, we get to chop off a lot of terms, right? Any terms containing W and Z gets chopped off, right? And the final row of equation gets written off as well. Okay. The next thing which we wanted to do, right? The next assumption which we wanted to make was for the flow to have no viscosity, right? An inviscid flow. So, in a flow which does not have viscosity, right? Remember I showed you this illustration where we have some kind of velocity moving the fluid elements in the first 4 rows, right? You're going to get this sharp velocity gradients, okay, for an inviscid fluid. Okay, and the role of viscosity or the viscous stresses is to smear that out, right? It's going to smear this sharp gradient away, and it's going to transfer some momentum away from these sharp gradients, right? Okay, so with viscosity, right, it's going to smear my sharp gradients, okay? Right, and you can see this velocity profile does not have a sharp gradient, but it has a varying, quite smooth varying profile. Okay, so viscosity basically smears things out. It is also known as the diffusion terms, right? So it diffuses all these sharp gradients away. Okay. Now, if you look at regions away from these high gradients, high velocity gradients, such as the region below here, okay, and the region above here, okay, viscosity is not that important, right? Because you don't have sharp velocity gradients in those regions. Viscosity is not that important. Okay. The other thing is when we neglect viscous terms, it means that we will not be having any flow separation, right? We don't have a boundary layer forming on the wall, and there will be no flow separation, right? And for a flow over a bluff body such as this, like a cylinder, that's not quite what is actually happening in real life, right? Because for a bluff body, you're going to have large separations at the back of the cylinder, right? You're going to have large wakes forming behind. So for bluff bodies, the effects of separation is very important, okay? But for this course, we want to see, or we want to understand the flow over an airfoil, right? And an airfoil is a streamlined body, right? Streamlined body, and the separation behind the airfoil is relatively minor, okay? So this assumption is, I guess, fairly valid, right? I know some of you are looking at me and you're not so happy, but you know, you're thinking that, oh, Leon, there's no fluid which does not have viscosity. It does not exist, right? An inviscid fluid is an ideal fluid which does not exist in the real world, okay? But if you don't believe me, at least believe Professor Albert. So in the 1912s, he mentioned that frictionless fluid has no existence in nature, but is hypothesized by mathematicians in order to facilitate the investigation of important laws and principles that may be approximately true of viscous or natural fluids. So it does not exist, right? Inviscid fluid does not exist, but for what we're doing here, right, the approximation is actually not too bad. Okay. Right. So we're going to get rid of all the right-hand side terms. Okay, and I'm going to expand some of these terms a little bit. So if you look at the continuity equation there, del rho u over del x, right? That can be expanded to rho del u del x plus u del rho del x. Okay, and that's basically just my product rule, right? Okay, so similarly, these two terms can be expanded into 4 terms, right? And let's have a look at this del rho terms. Right, so everyone knows what is rho? Density, yep, very good. Yep, so rho is density. So del rho del t del rho del x del rho, del y, these are all just changes in density with respect to time and space. Okay? So density gradients, basically. And we know that density is mass per unit volume. Therefore, density can only alter if the fluid is compressed or expanded, right? But for potential flow, for this part of this subject, we will be assuming incompressible flows, which means that density does not change, right? And this assumption is, I guess, okay for water, right? Because if I have water and I compress it by 100 atmospheres, the density is going to change only by 0.4%. So it's very, very small change in density. So water is incompressible, basically, right? But for air, if the flow of air is less than Mach of 0.5, it is considered incompressible, right? And Mach number is basically just the ratio of the speed of the fluid relative to the speed of sound. Okay? So if my air is moving at a Mach number of 0.5, it has half of the velocity of sound, right? So when the fluid is moving faster than Mach 0.5, it is considered compressible, and we get funny things happening, right? I'm not sure if you can see in this figure, but there are some lines. Can you all see some of the lines in this picture, right? You can see these lines here. Okay, and those lines are basically density gradients. All right, and these density gradients or shocks, which you'll look into more detail in part 2 of this subject, is caused when this airplane is moving at transonic or supersonic speeds, basically at high Mach numbers, right? Okay, but for this part of the subject, we're going to assume incompressible flow. So del rho is going to be equal to 0. Okay, this makes my life quite easy because all of these terms here, right, this one, all goes away. Now, I can factorize rho out from this equation here. Okay, and one possible solution is that rho equals to 0, okay, but water and air has a finite density, right? So therefore, del u del x plus del v del y has to be equal to 0. Okay? All right, now let's look at the momentum equations, and we want to get rid of the density terms as well. Okay, so if I expand all of these equations, or all of these terms, okay, density just falls off. Yep. Now, I'm going to look at the momentum equation in the x direction, and I'm going to expand it further. All right, so I have this del u squared del x, and this term del uv del y, right? And using the product rule, I'm going to get these 4 terms, okay? Now, if I take these 2 terms, right? Oops. What did I do? Okay, and I take out the u, right, in front. I'll get u bracket del u del x plus del v del y. Now, can anybody tell me what is this term equal to? Very good, right? So this term here is 0, okay, because remember from continuity, we found out that this term is equal to 0. So this whole term then goes to 0. And my momentum equation simplifies to something that looks like this. So I have del u del t plus u, del u del x plus v, del u del y equals to negative 1 over rho del p del x. Okay? And similarly, you can do the same or the momentum equation in the y-axis. Okay, but I'll let you go home and prove this yourself. Okay? So we started off with this massive equation, okay, but by assuming two-dimensional, inviscid, and incompressible flow, we are able to reduce the sets of equation to something more manageable, something more simplistic, all right, which is these equations here. And the momentum, so basically the first row, is the conservation of mass, right, and the second and third row is basically my conservation of momentum in x and y direction. Okay, and these equations are also known as the Euler's equation. Okay, and this is written in Cartesian coordinates. Right, so this is very important. There has been past year questions where you are asked to simplify the Navier-Stokes equation for a 2D inviscid incompressible flow. All right, so you need to know how to do this yourselves. All right, I can guarantee you in the exam, the first question is going to be a derivation question. Okay, which derivation? I can't tell you, but I will highlight the important parts in my lecture. Okay. Right. So we managed to derive the Euler's equation, or by simplifying the Navier-Stokes equation. Now we want to derive the Euler's equation from first principles, right? Just using conservation of linear momentum and conservation of mass. Okay, but before we derive it from first principles, I need to introduce you a new operator called the total derivative. Right, so let's say I have a fluid element here. Okay, and my coordinates x is on the right, okay, and y is on the left here. Okay, and let's say that this fluid element moves from some point A to another point A dash. Okay, so at point A, my velocity in the x direction is u, and my velocity in the y direction is v. Okay, and this fluid element has moved some distance dx and dy, right? Some arbitrary distance x and y, dx, dy. Now, my velocity, okay, let's look at the x direction. So my velocity in the x direction at point A dash is going to be u plus some change in velocity due to time, with respect to time, del u del t times dt, right? Plus some change in velocity with respect to space, right? Del u del x times dx plus del u del y times dy. Is that clear? Right, because velocity here is a function of space, x and y, and also time, right? And similarly for my velocity in the vertical component in y is going to be v plus some change in velocity with respect to time and some change in velocity with respect to space, x and y. Okay? Now, if I want to find acceleration, what's the definition of acceleration? Right, rate of change of velocity, very good. Okay, so it's basically the rate of change of velocity. So change of velocity divided by some small time, dt. Okay, so the change in velocity is basically these three terms there, right? So I'm going to take that, and I'm going to multiply all of these terms with dt. Now we're looking at acceleration in the x direction, by the way, okay? So the dt terms in the first term cancels out, right? We have this term dx dt. Can anybody guess what dx dt is? U, right? Velocity. Okay, so it's going to be u, and dy dt is v. Very good. Okay, so I'm going to get my acceleration in the x direction is going to be del u del t plus del u del x plus v del u del y. Okay? And again, you can show it by yourself that ay is going to give you del v del t plus u del v del x plus v del y. Right? So all you have to do is just change u here with v. Okay? So the total derivative, right? This operator is basically the total change of some quantity in both time and space. Okay? So the total derivative is is d over dt. Okay? And it's going to be equal to del over del t plus u del over del x plus v del over del y. Right? So basically this equation at the top here can be rewritten as du dt, and this equation for the acceleration in the y component can be written as dv dt. Okay? Everyone following so far? Yep. It's either that this is too easy for you or I've totally confused you. I'm going to assume that you guys are smart and you'll understand what I'm saying. All right. But if you have any questions, just feel free to stop me, okay? All right. So now with this new operator which we have learned, the total derivative, okay, we're going to try and derive our Euler's equation from first principles. Okay. So this is in page 13 of your lecture notes, by the way. Okay, you can refer it. So we're going to consider this fluid element here, which has some length dx and some height dy. Okay, and I'm going to do conservation of linear momentum, right? F equals to ma. So the total force in the x direction is going to be equal to the pressure force in phase A, which is the phase on the left here, okay, minus the pressure force on phase B, which is the phase on the right-hand side of that fluid element. Right, so the force acting on phase A is going to be just my pressure times my area, which is going to be dy times a unit depth, right, because it's 2D. So we don't have any z component, so it's just a unit depth. So we get P dy. Okay, and the pressure force on phase B is going to be equal to the pressure at phase B. Okay, so the pressure at phase B is going to be P plus some change in pressure. Okay, del P over del X times dx, right? Some change in pressure in the x direction. And again, it's going to be multiplied by the surface of that phase, which is dy times a unit length 1. Okay? Now, you can see that this term here and this term here cancels out. Right? And I'm left with fx equals to negative del p over del x dy dx. Okay? So that's fx. Now we're going to look at max. Right? And my mass, right, m is just going to be equal to my density, rho, of that fluid element times the volume of that fluid element. Okay? So I'm going to get rho dy dx. If you guys are watching at home, I'm sorry if I'm confusing you with the screen. Anyway, so that's your mass, all right, and ax is easy, right? It's just basically the total derivative of u, which we have derived earlier on, right? du dt. Okay, so if I put everything together, max equals to fx, I'm going to have something that looks like this. And you can see that I have dy dx terms on the left and right hand side, so I can cancel this out. And the next thing I'm going to do is I'm going to bring my density to the right hand side. Okay? Right, and that's how I derive the Euler's equation in the x direction, okay, from first principles. Right, and similarly, you can do it in the y direction. Okay, I'm just going to go through quite quickly here. Right, but you should end up with this Euler's equation, just as how we have obtained it by simplifying the Navier-Stokes equation. Okay, so very simply, just by using Newton's second law, we are able to derive the Euler's equation. Before I move on, are there any questions? Yep. Okay, again, this is a potential exam question. Okay? So in the exam, they might ask you to derive the Euler's equation from first principles. Okay? And you should be able to do that quite simply. Now, we are going to derive the continuity equation from first principles as well. Okay? And again, I'm going to consider a fluid element. Right? So, my velocity on the left of the fluid element is u, and on the right is going to be u plus some change in velocity with respect to the velocity gradient in the x direction, right? So velocity gradient in the x direction times dx, which is the length of the fluid element, right? And similarly, v, at the bottom is just v, at the top of the fluid element is going to be v plus some change in velocity with respect to the velocity gradient in the y direction, right? Times dy, which is the height of the fluid element. So we know that mass cannot be created or destroyed, right? Therefore, the rate of mass flow into the element has to be equal to the mass flow rate out of the element, right? Basically, whatever comes into the fluid element has to go out. So the rate of mass flow into the element, okay, you can see that there is flow moving inside the fluid element from the left. Okay, and that's just going to be rho u dy. And again, there's no z component because z is just a fluid, is a unit length, right? So it's just rho u dy. Okay, and at the bottom surface here, I'm going to have some fluid coming in as well. Okay, and that's going to be rho v dx. And whatever is coming in has to equal whatever is coming out, which is going to be rho plus my velocity u on the right hand side of the face of the fluid element times dy plus also the rate of mass flow rate coming out from the top of the element, which is going to be rho times v, the velocity at the top, right, times dx. And I'm going to cut off a few terms. Okay, you can see that on the left hand side here I have these two terms which are the same as this term on the right and this term on the right. So that goes off. And I end up with something that looks like this. Okay, and there are two potential solutions here. Rho can be equal to 0, but we know that air and water has finite density, so that's not a possible solution, not a probable solution, right? So it has to be these terms here equal to 0. Okay, and because there's dx dy in both sides, I can cut them off, and I'm going to get my continuity equation, which is d del u over del x plus del v over del y equals to 0. Okay? So you should be able to derive these equations from yourself, for yourself. Okay? So just to illustrate continuity, it basically means that whatever is coming in to the fluid element on the left from A has to come out from the fluid element on the right at B. Okay? But if I restrict the flow at B, right, the fluid has to go somewhere, right? It has to go somewhere so it can go out from the other faces of the elements if it's in 3D. Okay? Right, and if I restrict the flow at B, you can see that the flow at the other faces increases. Okay, so whatever comes in has to come out. Okay, so far we have been working in Cartesian coordinates, right? X and Y exist. But we should also look at cylindrical coordinates. How many of you have heard about cylindrical coordinates? Or have not heard? So everyone knows cylindrical coordinates, right? Okay, good. So sometimes in the assignment or in the exam or in the tutorial questions, it is just easier to solve the problems in cylindrical coordinates instead of Cartesian coordinates. So a bit of background on cylindrical coordinates. So if let's say you have some point P, okay, in Cartesian coordinates, I can express the location of P as a function of X and Y, right? And my velocity components U and V are along the X and Y axis. Now, in Cartesian coordinates, right, I can express point P as a function of R, right, which is the radial location from okay, I'll get a new adapter. I think it's my adapter. Okay, it can be expressed as a function of R and theta, right? Theta, which is the angle. Okay, and my velocities are UR, which is the velocity in the radial direction, and U theta, which is the velocity in the azimuthal direction. Okay? Right, and hopefully you all know the relationship between X and Y with respect to R and theta, right? So X is just R cos theta, and Y is equals to R sin theta. Okay? And you should also know the relationship, how to get UR and U theta from U and V. Okay, so U is just equals to UR times cos theta minus U theta sin theta, and V is equals to UR sin theta plus U theta cos theta. Okay? Right, so we have three options for getting our equations into cylindrical coordinates. The first one is you can just accept Nick's word about it, right? And you can just use these equations, okay, straight away. Okay, but where's the challenge in that? So we can rederive them in cylindrical coordinates, right? And we can also transform our Cartesian equations to cylindrical coordinates. Okay, because we are engineers, we love challenge, we are going to rederive them in cylindrical coordinates. Okay, so let's say I have a fluid element, right? Oops. So in cylindrical coordinates, let's say I have a fluid element, okay? It looks something like this. Okay, R is going to be the distance from the origin up to the left part of my fluid element. And d theta is going to be the angle of the fluid element, right? and my fluid element has a length of dr. Okay, and on the left face, that height is going to be r d theta, and on the right face, it's going to be r plus dr, right? So it's basically just this, right? R dr times d theta, which is this angle here. Okay. So I'm going to have a radial velocity going into the fluid element, ur, and on the right hand side here, I have ur plus some change in velocity in the radial direction, right? And similarly, at the bottom of my fluid element, I have u theta. Okay, and at the top here, I'm going to have u theta plus some change in the azimuthal velocity. Everyone clear so far? Yep. Okay, so conservation of mass, basically whatever comes in has to come out, right? And the mass flow rate at a given phase is going to be equal to the volume flow rate times density. Okay, and my volume flow rate is just going to be my area times velocity. Okay, and that will give me my mass flow rate at a given phase. And I'll find the mass flow rate at all 4 phases of my fluid element. Okay, so I think in this subject that it's good to all right, I think it's good that we do these derivations together, all right, not just listen to me babble along. Okay, so we're going to try and derive this continuity equation together, right, if this works. I always come prepared, so if it's not working, try a bigger one. Okay, doesn't work. I'll try not to shake too much. Okay, so as we do this question, help me out a little bit, all right? And if I make a silly mistake, please let me know, but don't embarrass me. Okay. I think those of you at home who are listening might be a bit blinded by the flickering lights. Oh, come on. Okay, this is not working out. I promise you that tomorrow it'll work. I think we have a lecture tomorrow, right? Okay, we'll do this tomorrow, okay? And I'll let you guys go early today. Only today, all right? Yeah, really sorry about that. I don't know what's going on. It doesn't really happen always. But yeah, we will do the derivation tomorrow at 11. Okay, so sorry about that. So del V over del T is the velocity change, right? Yeah. Velocity gradient, right? So So we need to multiply it by some time to know the change. It's the rate of change, sorry. This is the rate of change.
The rate of change.
So you want to know the change, you have to multiply it by time. That's the rate.
Same reason?
Yes, but this is for time, this is for space.
Yes. But
yeah.
if I have total derivative, like if it's total derivative like this, we don't need to multiply. If it's total, if it's not the partial, if it's total, we usually don't. Is it that right?
Total derivative. So total derivative is your acceleration, right? It's your acceleration. That's why there's no dt there.
Yes.
So you know total derivative is this is bad. I don't know why it's not working.
Maybe the adapter.
Yeah, I think I have to change this. It's really annoying. Sorry. So the total derivative, right, is so this is your acceleration, right?
Yes.
So the total derivative is going to be, right? Total derivative is just del over del t plus u del over del x.
Yes,
plus
yeah.
v del over del y. Right? But this is different. If you want to express your velocity here, it's going to be v plus the total derivative, right? du over dt times dt.
Yeah.
Yep.
Yes. That's clear.
So then you have to multiply by dt, then you get the same thing.
Good. Thank you.
Yeah.
Thank you so
Okay.
much.
All right. No problem. Yep. Hey.
So, hi, Liam. I just want to know
Yep.
what you're teaching here right now.
Yep.
The lecture is that was already uploaded or after the lecture?
I'll try and upload it after the lecture. Yep. I know some of you want it
Yeah.
before, right?
Yeah. The which is
Yeah, but maybe starting next week I'll try and upload it in advance. Yeah. Because it's a bit hard because I don't know when I'm ending my lecture. Like today, you see, I end a bit earlier than I wanted to.
yeah.
So then, it's a bit hard for me to upload the lectures without me knowing until which topic I'll be covering.
So the one currently is potential. So
Yep.
that potential flow is based on just only the lecture slide type. I mean, so many pages like that one you told me in that was 13 pages of the whole lecture. So just only
That part.
it cover.
Yes. So we jump a little bit in the lecture slides. Yeah, we don't follow exactly. We jump here and there a little bit. Yeah.
So just for LMS, just only one lecture, and also just only for one lecture.
Yes, at the moment I've only uploaded the first lecture.
Okay.
Yes, but the lecture notes should be there. Yeah, the lecture notes should be.
Yeah, that's just
Just
lecture
lecture
notes
notes,
is so many pages.
Yes.
I mean, I just find it out and also you just jump to the other part and
Yes, so the lecture notes jumps a little bit, but that's the best reference, I think. Yeah, that's a good reference to start with.
okay.
Right.
Is that
Yep.
the same as like energy in, energy out for the real shell energy in the thermal? Like and cannot be destroyed or cannot be
I think it's a bit different, right? Because energy has enthalpy and
entropy
but I think we don't it's similar, but we don't consider the entropy and all that here. Yeah, you'll see that the energy equation, right?
yeah.
Yeah, this is momentum, not conservation of energy.
Oh, okay.
Yeah, so it's a bit different, I think.
Yeah. So yeah.
Okay. Okay, sure.
I just want to know, like, how many people can we have in a group for the assignments or anything? Two.
Yeah, it's 2 or 1,
All right. Okay.
unfortunately. Yeah. So
I'll just mail you regarding the practical. I'm not able to sign into any of the classes.
you can't
No, it's not showing on the timetable.
for 1 or 2.
For what?
1 is the MATLAB session.
MATLAB, yes.
Okay. Yeah. I'll see if I have enough people who give me the response. If there's enough, I'll try and open. If there's more than probably 15 or 16, I'll try and open another session.
Right.
But if I don't get more than 15 or 16, then most likely you might have to just rock up to and bring your laptop.
Yeah, thank you.
Okay, no problem. Yep.
I have some questions about
Yep.
the lab.
Yep.
We have the practical 1, practical 2, and
The lab is the practical 2.
Yes, the F1 lab, correct.
And I know the lab is start from week 3 to week 8, and I have registered practical 2 on Monday's afternoon. And should I go to the lab each week, or I just went there once?
I told you in the lectures.
Yes, but a little.
You didn't get.
I suppose I could just go to the lab once.
Yeah, okay. Just for you, right? I'm going to repeat one more time. Once. Sorry. That's good. So, okay. So, P02 is your F1 lab, right?
But I cannot get this page from my
Really?
LMS. I cannot get this page.
If you just Google, I think Melbourne timetable system, then it should come up. And then you just put MCEN 90008. Then it has the whole timetable. And then you should be able to see the date. So if you're in 14, it should be 20th August.
It means that I do not to select my date. My date. I mean to go to the lab and.
No, because if it's 14, so like there's so many right in the same week, but they're all different
this
numbers.
number is determined automatically, or
You can select the number.
I can select a number and I can select a date.
The number you select would correspond to a certain date.
And in this case, I can select my group. I mean 6.
No, you can't. So whoever who registered until it's full, then that's it. Yeah.
And for lab report, could I select my partner
It has to be from the same lab.
from 6 people?
Yes. It has to be from the same.
If I select number 14 and my friend select number 15, and we can.
You can't, because the due date of the labs are 3 weeks after your lab session. So if you do it on a Monday, right, and your friend does it on a Friday,
Both my friend and I get the practice 2 on Monday's afternoon, and if I get the 14 and 15, and we can do the lab together, and we can.
it has to be in the same group because of marking. Yeah, marking logistics. Yeah, because I think if you do your lab later, you have a later submission date.
And if I do the lab at the week 3, and I should submit my lab report at week 6.
6, I think. Yeah. But the demonstrator will tell you in more detail. Yeah. If you need an extension, you might be able to give.
And I have another question. I have read something about the lecture note in this subject, and if I get some questions, I mean some derivations that I cannot understand exactly, may I ask someone like tutors by email? And I can.
Yeah, you can ask me or you can ask the tutors. Yeah, no problem. Yeah, but tutorials only start week 3, I guess. Yeah, so until then, if you have any questions, you can ask me. Yep.
Excuse me, do you have to know the process of the formula, of like this? The process of the formulas. Do we need to write down?
Yeah. So you have to know how to derive it. Yeah. So you need to know why there is some change here, right?
Yes, I also want to ask why we need to add this change.
Because U is a function of space and time, right? So in this case, we are assuming the same time, but you have moved in space, right?
Yes.
So you're going to have some change in velocity.
In velocity?
Yeah.
Right. But why need to plus the dv to the x?
The x is because you have moved this distance.
Distance?
Yep. So this is the fluid element, right?
Just like the velocity equal to how to say? And this is the time, and this is the like the
Acceleration times time.
Yes.
No. It's different. So
Why
this one is
difference? But u means the velocity.
U is velocity.
Velocity,
yep.
right?
Velocity. Yep.
But the u plus
So here is U,
yes,
which is this U,
Yes.
plus some change in U. Some change.
Changing.
Yeah.
But this U is not equal to
This U is same as this
This
U,
U.
but the velocity on this face is going to be this U plus some change.
plus and change.
Some change. Yeah.
All the change.
Yeah. So this is actually delta U. This is
Okay.
delta U. Yeah. Some change.
Some change.
Because your velocity change, right?
Right? Yes.
With space, x and y,
Y.
and time. So here it's moving in the x direction. So U is going to change with x.
Okay.
Yeah.
I see.
There's some changes in the velocity, and I just write it. Yeah, that's that.
Okay. Thank you.
Yeah, I was wondering, could you put the lecture slides up before the
Before
actual
the lectures.
Yeah, because it's very hard to follow. Because the actual lecture notes from the previous lecture, it's like it doesn't have all those equations, so it's a bit hard to follow up. Especially when you have to write it down, because I mean you went a bit quite fast, so you have to write it down, it's a bit hard. So
Okay.
yeah, just maybe. Could you?
I'll maybe not this week, but I'll
Yeah.
try for next week. But the thing is, right? The problem is that I'm not sure how far I'll go in the lectures. So if I upload the lectures in advance, right, I might not cover or might cover more materials than expected.
Also, you scared you cover more than what you upload.
Yeah.
Then also, do you do lecture slides as you go through the week?
Well, I have a few. I guess I have a few lectures which I have draft.
Oh, okay.
Yeah, but I'm afraid if there's a question or something, then my lecture might go slow or faster.
Yeah, I know. I mean, I thought you had all the lecture slides prepared, so you can just upload all in one shot.
You
then
want
just-
you want it?
Yeah, because I think it'd be easier for
Really?
us to follow. Yeah, because maybe not me alone. Maybe some other people might have the same concerns.
Okay, I'll try and release the lecture slides 1 week.
Yeah, because it's easier to like read and follow at the same time. Because like now the one that we printed out doesn't really have the formulas that you gave. So we were like,
Okay. Yeah. Okay. For next week, I'll try and upload it before the
Let me
lecture.
just upload like all one shot so we can print it all one shot. And
Everything?
No,
No.
maybe I'll like.
It'll be too out of sync.
I mean, we can just print it. We don't have to use it, right? We can just print it beforehand. Then come to class. What you teach, we can just follow.
Sure.
Maybe just like.
Okay. I'll try and do that next week. Okay. No problem.